Hello. So I'm continuing on page number 11 in your notebook in the note taking guide. We have learned about radical functions and the equation of circle in the previous video. Now we are looking at some functions that are related to radicals, okay, related to the square root function in an indirect way, and I'll talk about that now. The parabolas that have horizontal x-axis, okay, parabolas with horizontal axis. So you see this parabola here, and its axis is the x-axis, right? Axis means the line of symmetry, okay? And this parabola, just like how, if you have a parabola with the vertical axis, that has equation y equals some x square. This parabola will have the equation x equals something y square. Okay, the standard one would be just x equals y square. But if you are stretching it, or shrinking it, it would have some coefficient there. This x equals something y square is rewritten like that. Y square equals 4cx. That something could be, taken to the other side and divided, and you can rewrite it as y square equals some constant x, because we want to keep y on the left side, as the function, right? As the not function, as the output. X is the input, y is the output. So y square equals something x. And I highlighted here in the top that it's not a function. You can clearly see, that the parabola with the horizontal axis. If you draw a vertical line, it intersects at a positive value and a negative value, right? So it fails the vertical line test. It is not a function. For the same input x, you have one output up there and another output down here. So that's not a function. But you can easily see it is made up of two functions. If you just slice it at the horizontal axis and consider only the part above, it's a function. Or if you consider only the lower part, that is also a function. So it's like two functions which have been put together like that. Okay. All right. Now, what are, some telltale signs of the graph? If the graph is opening to the right side, then for positive, then it is defined. Then, okay, if it is opening to the right side, then for positive x, the y values will exist for positive x, right? It is on the right side. So in that case, that c has to be greater than 0. X is positive, c is also positive, hence you get the parabola on the right side. Okay. And now, by the way, the vertex is at the origin. Okay, so if you plug in x equal to 0, y will also be 0. So the vertex would be here at the origin. And if it is opening to the left side, in 4cx, look at that, like right side, 4cx. Now the x values are negative on the left, but on the left side you have x y square. So that means overall, this you want the whole quantity to be positive. You want that to be positive, otherwise you cannot make it equal to some square. X is negative, so how can you make the overall expression positive if your c is also negative? C is negative, x is negative, so when you multiply negative and negative, the full expression becomes positive, and that makes sense because it's y square on the left side. So in summary, if C is negative, you open to the left. That means the coefficient of X. Okay, so when I say C here, you have to think as coefficient of X. If the coefficient of X is positive, you open to the right. If the coefficient of X is negative, you open to the left. Okay. All right. Let us do some example. Now we are moving on to examples, of course, which are not necessarily centered at the origin. This is the graph. So first you look at x equals y square only, and clearly that will be a graph like that, opening on the right side, or y square equals x, right? It's opening on the right. Then you are saying -3. You have to understand here. Okay, there are two ways of looking at it. According to our previous understanding, I would have brought that -3 to the left. I'll talk about that in a second. I'm talking about the new understanding of thinking of x as a function of y here. Okay, x equals y square minus 3. So I have x equals y square, and then I have to do -3. -3 on what? The output. Okay, so the x, ultimately the x becomes less by -3. So now this action is in the horizontal axis, not the vertical. This graph that I have drawn here is x equals y square. I'm now doing -3 on what? On x. So I'm going to move it 3 units to the left. As I said, now don't mix up this with what we were talking earlier. Earlier we said -3 means it will take it to the right, but that was when y is a function of x. Here x is a function of y. Okay, so when you plug in 0, for example, in this graph, when x is 0, your y is 0. But now it is when in the given function here, if you plug in 0 for y, your x will be 0 minus 3, right? So you need to go to the left. So for our equation here, which is x equals y square minus 3, your vertex will be at -3, 0. As you plug in 0 for y, x becomes -3. Okay. Now that is a way of understanding this graph. If you want to understand it in our previous way of looking at y as a function of x, I would write this as y square equals x plus 3. Okay. Now y square equals x is the red graph there. And we remember from our earlier discussion that if y is a function of x, then x plus 3 will be the left shift. Plus 3 means left, right? So you'll shift 3 units to the left. Whichever way you want to see, okay? Get the understanding clearly. Okay. Next. X equals 2y squared. So like before, first let me draw the original graph. The parent graph will be x equals y square. Now suppose we are doing 2y square. Then the values of x are becoming 2 times, right? Think about it. For the same y value, the value of x is 2 times. So this is a horizontal stretch. That would be your x equals to y square. How do I explain? You have to get convinced with this. Okay, this is horizontal stretching because you are multiplying the values of x. So for the same y value, your x value should become larger. So you have to go further to the right. So it is a horizontal stretch. You can also get the same output or the same output graph if you think about it with reference to some particular point. Okay, for example, When y square, when y is, I'm trying to see, a suitable value of y. Let's say I take y equals root 2. Okay, when y is root 2, x will be 2 times root 2 squared, which will be 2 times 2, which is 4. Okay, so the value here would be 4 comma root 2. Sorry, in x equals y square, it will be just that 4 comma root 2 is not there. Bad. 4 comma root 2 is will be somewhere here. Okay, but in x equals y square, that root 2 squared would just have given you 2. Okay, so x would be 2 for the same root 2 here. So when x is 2, y is root 2. And maybe on this one also I should bring my thing a little down. Root 2 here. Now I'm to indicate the fact that it's the same y value, y height, I'm going to draw this dotted line like that. And of course my graph will continue above like that, like that. Okay, at that height root 2, y value is root 2. In x equals y square, it will just be, x value will be 2, so 2 comma root 2. In x equals 2y square, it will be 4. So you go to 4 comma root 2, right? So for the same y value, you have to go more to the right. So it is a horizontal stretch. Okay. All right. Going back to our older method, just so that you understand that way also, you can write this as y square equals half x. Right? Now, if you remember in our vertical way of thinking of the scale, if you are doing half x, then you are vertically shrinking. So vertical shrinking is same as horizontal stretching. Okay. Next, sketch this. Now you get more or less the picture, when you are sketching this now, we are going to think in terms of all the actions that are applied in the original graph. The original graph is, the parent graph is x equals y square. What has been done to that? Okay, that will give you this new graph. Okay. Like we have done before, you can write the sequence of steps as, first you are making it, instead of y square, you are doing 3y squared, right? Let me see. Okay. Okay. Previously, I did in my previous example where I did, y square equals, sorry, y square, y equals under root 4x plus 16 plus 4. Like in one of the previous videos, we did that function. There I talked about the scaling first. In this one, let me do the shifting first. Okay, just so that you can see, there are different ways of looking at it. Now, if I want to do the shift first, I have to rewrite that function a little bit. Okay, otherwise it will not be convenient. It will not be clear. It is 3y. I need to make sure that it is just y minus something, not 3y minus something. So I'll take 3 as a common factor. It's 1 over 2. In the parenthesis, I'll take 3 as a common factor. So it will be y minus 2 over 3 whole squared plus 4. Okay, I factored the 3 out of it. And now it's the whole square applies to both 3 and the other factor. So 3 square will be 9. I'm going to write it outside. It will be 9 over 2. Y minus 2 over 3 whole squared plus 4. Okay. Now you can think in terms of shifting first. Okay. So this equation, I would say the steps. The first step we did was y minus 2 over 3. Okay. You have to think differently from how you have been thinking of the y as a function of x. Okay. Like, we have been talking here. X is a function of y here. So when you do y minus 2 over 3, okay, you are subtracting the y value. You are subtracting 2 over 3 from the y value. So wherever your original graph was x in terms of x equals y square, now you are doing y minus 2 over 3 squared. Like now you are basically what you call your y values are going down. Okay, that means in your graph, okay, in your graph, the new vertex will be 2 over 3 units below, down. Okay, so I would say shift 2 over 3 units downward. Okay, I just make sure that I'm saying this correctly. Or, oh no, should I say down or up? To get the same 0 for x, I should go to 2 over 3. I'm sorry, not down. The logic applies up. Okay, let me explain this way. Why should I say it should be 2 over 3 units up? Because if you plug in 2 over 3 for y now, then you get the x equal to 0, compared to y equals x square, x equals y square, which would be 0 at 0. Now you have to go to 2 over 3 to get the same 0. So you're actually your graph, in that sense, okay, the graph is moving up. Okay, so 2 over 3 units up. Okay, there's one more way of understanding why it is up here. When y is a function of x, then the action on x has opposite effect, right? If you subtract an x, it was moving right. If you add an x, it was moving left. In the same way here, when x is a function of y, the action on y has opposite effect. If you do y minus 2 over 3, you are shifting the graph up. Okay. And then you scale or stretch. I mean, scale means stretch. Stretch how? You are multiplying, basically you're stretching horizontally here. Okay. Stretch horizontally by a factor of 9 over 2, 4.5 times. Okay, you scale it stretch it 4.5 times. And then in the third step, plus 4. Now this is on x. Okay, the y square value, then you have to, now your new x will be plus 4. So move 4 units right. Okay, those are the operations on that original x equals y square on this graph. Okay, let's use that understanding and draw the graph now. Sketch the graph. So let me see. Shift up, stretch horizontally, and move right. So I think I can sketch my graph like that here. Let me draw the dotted one for the parent graph. Okay. This is y equals x squared, and I'll change color. So you are shifting it to 2/3 units up. So in the first step, let's say this is 2/3, and here you have almost here would be 1. So first you moved to your 2/3 units up, and that graph is not y equals x square, sorry. It was x equals y square here. So this graph would be x equals y minus 2/3 squared. Okay, so a small correction in the way I draw the graph. It should intersect the x-axis when y is 2/3, x is 0, that's fine. And when does y become 0? Under root x at 4/9. One second. Plus minus root x, 2/3. 4 on the square root of 4/9 will be 2/3. Okay. So I'll do it like that. Eventually, anyway, it will cross the x-axis. So where does it cross? I was just trying to find the x-intercept. My understanding is it should be at 4/9. Okay, when I plug in 4/9 for x, or when you plug in 0 for y, okay, that's the easier way of thinking. If you plug in 0 for y, you get 0 minus 2/3, which is minus 2/3 whole squared. That becomes 4/9. Okay, so when x is 4/9, y is 0. And when y is 0, once again, sorry, what am I saying? When y is 0, x is 4/9. And when x is 0, you have y minus 2/3 whole squared equal to 0. So y equals 2/3. Yes. Okay, that's right. So you have the x-intercept and the y-intercept here. Okay, that would be the intermediate step. Now you are stretching it horizontally by a 4.5 factor. Okay, and that one I will do it in a yellow color. So you are stretching it horizontally. So you are going to get a graph like that, which will get stretched like that. And then you are moving 4 units to the right. Okay, so 4 units to the right, I don't know. Let's say if it takes me somewhere there. Finally, the main graph, I'll draw it in solid and would be somewhere there. Okay, and that equation would be x equals 9/2 y minus 2/3 squared plus 4. Okay, and the vertex, by the way, if you ask me where is the vertex, x is 4, y is 2/3. Right? So it has been like stretched, and then this is the dotted line, this is the axis. Y equals 2/3 is the symmetry, line of symmetry. Okay, and you moved 4 units to the right. So 4 comma 2/3 is your new vertex. Okay, so replay this video and understand the various transformations that have been done. I'll repeat here orally. X equals y square, the parent graph. You moved up by 2 units. So it becomes x equals y minus 2/3 squared. Okay. Then you stretch it by a factor of 4.5, like 9/2, by a factor of 9/2. So it becomes, you're stretching it horizontally, so you get that yellow graph, which is much narrow looking, Then you do +4 on the x values, so you're moving to the right. And you have the new vertex at 4, 2/3. Okay? All right. So please do the homework problems after that. And in the next video, we are going to get into the last section of this chapter, which is solving equations and inequalities involving roots. Okay, I think I would not want to start that in this video. I'll see you in the next video. Thank you.